Graphs of polynomial functions. We've seen lots of graphs of different kinds of polynomials, so part of this is going to be a review, but most of it's going to be new. We've never really talked about it in terms of end behavior. We kind of have, because we've talked about rising versus falling when we talked about lines. And then snake and W aren't real math vocabulary, they're just a way that I've known math teachers, myself included, to talk about some different graphs. The biggest question I really want you to think of is, how does the degree of the polynomial affect the graph? And look for ways that you can categorize things. We'll talk about end behavior. That'll come into that categorization. I'm going to leave the talk about tables for right now. So we've talked first this year about linear equations, first degree equations like y equals mx plus b, that's standard form, and m served an important role. It's what told us how the line pointed, sort of, right? B was the y-intercept, and this is what told us whether the line rose if it's positive, or fell if it's negative. So if I have y equals 2x, it goes up this way. Very quick sketch, don't check my accuracy. And if it was y equals negative 2x, it went, again, not super accurate, but that would be a straight line, not a squiggly line, that went down like that. And if I changed it to y equals 2x plus 3, we get the same thing, but it crosses the y-axis at a different point. Again, let's make that a little straighter. A little bit straighter. So the y-intercept just moved it up and down the y-axis. The slope is what made it fall or rise. Now let's move on to the next type. Next we had quadratics. Spent lots of time on quadratics, standard form, or we can look at the parent function. But when we look at standard form, what did C do? What did that number on the end do? That was the y-intercept. And so I'm just going to do, let's say, y equals x squared plus, well, we'll just go with 3 again. So crosses the y-axis at 3. And then rough sketch on the shape, it looked like that. Okay, not perfect, but roughly like that. When we look at the similar thing, but with a negative in front, same y-intercept, and I could do a different one just to show you a different perspective, but only thing that made it open downward was that negative in front. So the leading coefficient, when we talked about lines, it was our slope. When we get into quadratic, it's just the number in front. It was our a. So it was m initially, then it was a, but it served the same purpose. So we called this one opening down. It had a maximum. Called this one opening up. It had a minimum. So now we're going to get into, this was second degree. Now we're going to get into, you guessed it, third degree. Now we're going to have cubic functions, third degree. And I'm just going to stick with y equals x cubed. If it had a number after it, that would be its y-intercept. I'm just going to do a very rough sketch. And I'm exaggerating it a little bit. So they look something like that. That is a horrible, horrible drawing, but you get the idea. They still rise up to the right. And if we have y equals negative x to the third, now, again, going through there if there's no constant. So this one falls. So what does this have the most in common with? Is it like a quadratic? No, it's very much like a line with a bump in it. Right? It's like a line is a stretched out piece of string, and now it's a little loose in the middle. And these are affectionately referred to as snakes. That is not a mathy term, that's just what we seem to say. And last we have quartics. And we could keep going, but we're going to stop at 4 because you're going to see the pattern. Quartics are 4th degree. So if I have y equals x to the 4th, and I'm very much going to exaggerate this. I'm not going to try to make up an exact equation. And why do well, I'll go ahead. Why do the 4th really kind of looks like a parabola but with a flat bottom? Kind of a straight line there at the bottom. But most quartics have more bumps in them. And they get affectionately referred to as W's. And I shouldn't say most, I should say many, because they come in all different types. But what do you notice the common thing is? What am I making a point about? What are they most like? They're like quadratics. They open up when that leading coefficient is positive, and if it was negative, again, the parent function is kind of boring. It's like a parabola with a flat bottom. But if we say many or most quartics with a negative leading coefficient, well, that didn't work out well. coefficient, negative leading coefficient, are still like a W, but what's different? Now they open down. So, first degree has something in common with third degree, and second degree has stuff in common with fourth degree. So what do these all look like? Well, this is just a recap of what we've done, but I'm going to talk about end behavior as well. We've talked about this is going to rise, but that's because we read from left to right. So when we say that this rises, think about the fact that this is rising as x is getting bigger, y is getting bigger. And as x is getting smaller, y is getting smaller. I'm going to write that in words here. We'll talk about notation for it. But as x is getting bigger, y is getting bigger. And as x is getting smaller, y is getting smaller. When it falls, it has the opposite relationship. Now, as x is getting bigger, y is getting smaller, right? X is getting bigger, but y is getting smaller. As x is getting smaller, y is getting bigger. And that's the same whether we're talking about linear with an odd or our snaky shape. Let's make a prettier one. Right? That's still the case on an odd degreed polynomial. As x gets bigger, y gets bigger. As x gets smaller, y gets smaller. But if it's negative, the opposite is true. Let's say x here is 5, y is negative 5. X here is 4, y is negative 2. Right? It's the opposite. Now we're over to quadratics. These are a nice vase shape, rounded on the bottom, and the opposite. I'm going to do the pictures first before we do the words on this one. Those pictures, and then these exaggerated compared to the parent function, but W-shaped and W-shaped. And each of the humps of the W can be big or small, almost non-existent. But here, as x gets bigger, y gets bigger. As x gets smaller, y gets bigger. Now that sounds like it can't be, but that's because there's this turning point here. And so we're only talking about the ends here. In the middle, all kinds of crazy stuff's happening. But again, this is talking about end behavior. And we'll look at different notations for it. I want you to think about it in words first before you get caught up in the notation, right? Reminder, we're talking about end behavior here, not what happens in the middle, because on a line, doesn't matter whether we're talking about the middle and the end. But when we're talking about a cubic or a quadratic or a quartic, crazy stuff happens in the middle. But if we're looking at the ends, as this goes up, x gets bigger, y gets bigger. X is getting smaller as we're going to the left, y is getting bigger. And on the same thing on the quartic. When they're flipped over in the reflection in the negative a, now as x gets bigger, y gets smaller, and the same thing with the y. As x gets smaller, y gets smaller. So look for some similarities and, compare and contrast there what the takeaways are. See how you can kind of fit that into your understanding. Again, we'll talk about notation, but I want you to think about it in the words. This is going to be really important in some things we do down the line. So really want you to think about it. There's a big polynomial function. How are we going to graph it? Well, we could graph it from a table, and we will do a couple from a table. Can you always do a table? Absolutely. You can keep plugging in x's, cranking out y's, because it's a function, it's a machine. You keep feeding it x's, it'll keep spitting out y's. Should we? Not very often. As long as we know the y-intercept, we know it's going to be a w, and it's going to open up. We know, I don't know where the y-intercept is going to be on this. But if I had to pick it out of a group, I could. Now, if I wanted the detail, I could always do a table. And we're going to do a few, but almost always I'm just going to ask you for a rough sketch. So you need to be able to tell me the degree, the leading coefficient, the y-intercept you should, and then a rough sketch. Again, We'll do a few complete tables. I'll tell you which x's to plug in. Does that mean those are the only x's? No, that means I'm just trying to save you time. Can you plug in more x's if you want? Absolutely. Can you plug in any x's? Sure, it's a function. But I'm going to give you enough guidance that you can do it. But more often than not, you're not going to have to graph these by hand. And most of the next couple chapters are going to be how to efficiently figure out the parts of this that we want to know so we don't have to go through a bunch of work to graph it.